Hello everyone, I'm Charles de Cagario. I'm a researcher at the Bristol Composite Institute from the University of Bristol, and today I'm going to talk about the relation of my work to soft robots. The presentation is called 4D Printed Biocomposite Soft Robots, Humidity Actuation, Material Selection, and Design. This research was conducted over my PhD and as a postdoctoral researcher, and has been sponsored by DSTL, EPSRC, and ERC. And I'd like to thank all my supervisors that are written on this slide for their support through this work. The soft robots, if you look at the definition, basically are robots which are made out of compliant materials, very soft material, compared to as opposed with metals and stiffer materials. If you look at Wikipedia page about soft robots, you can see that the control is made in 3 different ways: electric field, thermal control, or pressure control in case of inflatable soft robots. There's always one which is forgotten, and it's humidity. And that's what we're going to talk about today, soft robots which are actuated with humidity. The one of example of soft robot that exists in nature is pine cone, because the pine cone open and close depending on the surrounding environment. It's natural selection mechanism that has been made so that the pine cone reaches its seed at the optimal time in order to be able to spread as much as possible. The way it actuates is due to the bilayer structure of its scale. So if you isolate one scale, you have a scale which is made of bilayer structures with similar polymers, and there's different holes inside the different layers of the scale. So in one of these layers, holes are going to be a cylinder and in spring shape, but in the other layer, it's going to be a square shape and a smooth. And this difference of holes, as highlighted by Zhang and al., create different of properties interaction with humidity and the surrounding environment. And therefore, one layer wants to expand quite a lot, whereas the other one doesn't want to expand that much. But these two layers are bonded together. So the difference of sort of wheel of expansion between layers create stresses at the interface of the layer, and therefore bending. And that's how you actuate, open and close a pine cone. So if you think about this, the time it takes for the pine cone to actuate can be considered at the fourth dimension, at the dimension basically. So if you 3D print that kind of part, it could be considered at the 4D printed part, and that's why we call 4D printing that kind of actuating structures. So the thing I'm going to talk about today is mostly based on literature review that we published and called Design of 4D Printed Hygromorphs, State of the Art and Future Challenges. And so we're going to discuss different elements, which are the type of actuation, material selection, conditioning, mechanical properties, speed, repeatability, design, modeling, and printing path. And we're going to illustrate all these elements with a test that we've conducted in the past. So there are two types of shape that are available with 4D printed soft robotics actuators: bending and twisting. Bending is the one that we've explained with the pine cone scale, and twisting is a material curling on itself. Usually, the actuation that you will get from 4D printed hygromorphs is based on a combination of these two. In the presentation today, we're going to focus mostly on bending. So there are different ways of accounting for the amount of deformation you get out of your actuation. So you can have multi-parameters measurements, which are when you measure the displacement or the position of your actuators at all time and through its entire length. So you have a precise understanding of the position of your element through times of every single point, basically locally. Whereas you also have single parameter actuators on the right side of the screen, which is one parameter which accounts for the general deformation of the actuator. We can have eta, which is a deflection, alpha, which is a bending angle, and kappa, which is considered usually as a curvature. So I show this slide mostly because I want to explain what kappa is. It's the curvature, so the amount of general deformation that you get inside your material. We're going to see it a lot in this presentation, so it's important to understand what it means. So there are three types of structure actuation that are available. Two based on composite materials, and the third one, C, is considered as B material structures. So the B material structures is made so that you have different materials which are distributed differently between the different layers. These two different materials have different interaction with humidity. And therefore, if you distribute them differently in the different layers, you are back in the situation of the Pinecone scale, because the layer wants to expand differentially one from the other. Therefore, you create stresses at the interface and bending of the entire structures or twisting of the entire structures. That's how the actuation works. But I am from the Bristol Composite Institute, so I'm going to focus in this presentation on composite materials. And for these materials, you don't really care about the distribution of material. What you care about is the orientation of the material. So the composite material we consider are called orthotropic, meaning that the property inside in the direction of the printing of the fiber, is different than the direction transverse to the fiber. So if you have orientation different from different layers, we'll be back to the situation we've seen for the Pinecone scale, because the will of expansion of the different layers will be different in different directions. And therefore, you can get the bending. For instance, in the first image, you can see the second layer is horizontal, whereas the first layer has an angle. So if the fiber wants to expand most in the transverse direction, the second layer is going to expand a lot in the length direction of the specimen, whereas the first layer is going to be at an angle compared to the length of the specimen. And so you will create different actuation between the different layers and bending and twisting, as we've seen before. So the same thing with short fiber composites. So first and second A and B are continuous fiber composite and short fiber composites. Examples of such materials are the continuous flax fiber reinforced polylactic acid and the short flax fiber reinforced hydrogel that we've used in the past. So in the literature review we defined two different concepts for composite actuators. One is fiber-dominated actuation, and the other one is matrix-dominated actuation. So fiber-dominated actuation basically is the fiber that responds to the humidity triggers. So the humidity goes to the fiber absorbs the water, and then the fiber changes its morphology, with the absorption of water. So it's going to push or pull depending on if the amount of humidity increases or decreases. By pushing and pulling on the matrix, it creates the overall deformation of one layer, and therefore the actuation of the overall structures. For the matrix-dominated actuation, it's a bit different. It's a matrix that expands and contracts, and the fiber is here to prevent the deformation from happening in certain direction. So in the direction of the length of the fiber, the fiber is going to be capable of preventing the deformation from happening. So the matrix wants to expand in all directions. The fiber prevents deformation in certain direction. So if you 3D print in different direction, you can have the same actuation that we've seen on the previous slide, but because of the fiber preventing the deformation happening in certain direction. So the fiber-dominated actuation, an example is a flax fiber reinforced PLA, because the flax fiber wants to expand and the PLA not so much. Matrix-dominated actuation could be the flax fiber reinforced hydrogel, because the hydrogel is going to expand and contract a lot, while the flax fiber does not expand and contract a lot relatively to the hydrogel. They expand and contract, but it doesn't have so much of an impact. So you can see on the right side the example provided for these two materials. Then we can talk about conditioning. So how do we create a change in humidity in the lab? So it's a two-step process. You have a reference stage where you wait for your specimen to be at a specific actuation, and then you actuate by changing the humidity. So you can use air, oven, water, passive desiccator, active desiccator. The most common is air to water and water to air, because you get a large actuation very quick, and you are able to see the actuation of your material very efficiently. However, there is only one humidity available, and there is not a very good repeatability, because when you talk about humidity conditioning, the temperature has always an influence, and therefore it can impact the actuation that you can get. And controlling it, actuating in the air does not allow to obtain that kind of control. In order to have more relative humidity capable, you can use passive desiccator, which are boxes in which you have salt, and this salt controls the humidity inside. And therefore, you can have different ranges of humidity in order to see how the humidity influences the actuation of your material. And then you have active desiccator, in which you can usually control the humidity and the temperature at the same time. And you don't need to open and close the box to change the humidity. So basically, you can have a very precise control of the actuation of your material. So that's how you create actuation for your material, particularly in the lab. And in terms of material now, the actuation is related to the mechanical properties, because the stiffer the material is going to be, usually the more difficult it's going to be to actuate it, because you're going to need to have more stresses at the interface between the two layers to create the actuation. However, so through the work that we've conducted in the lab, we've been able to show that different material could be used for that kind of actuation. So from the left to right, you have databases which concern alginate-based hydrogel, short fiber 3D printed composites, and long fiber 3D printed composites. And for the stiffness E1, so basically the stiffness of the linear part for the stress strain curve for these different materials. And the red arrow presents the tests that we've conducted in ourselves, an estimation of the values that we got. So we got about 0.1 gigapascal for the alginate-based hydrogel, about 1 gigapascal for the short fiber 3D printed composites, and a bit less than 10 gigapascal for long fiber 3D printed composites. So you can see that you can have different range of stiffness for the material. All these materials were also tested for 4D printing, so you are capable of obtaining actuation for all of these materials. Basically, the mechanical properties are going to be important to understand, because your material wants to deform, but it also wants to interact with its environment. So you need to give it a specific strength, so the stiffness, so that it could achieve its purpose in its multifunctional abilities. So for instance, alginate hydrogel might be used inside human bodies, so it's very soft so that it doesn't damage the body. Long fiber might be used in order to carry some load, which is very different than being used in the human body. So yeah, depending on which material, which type of application, you might change different material, but you have a wide range of properties available. So all these databases are available in the paper that are highlighted here. I encourage you to have a look if you're interested. Another aspect that we wanted to discuss is the mechanical properties influenced by the porosity of the material. And when we started working on natural fiber composite, there was no clear guidelines in order to measure the porosity of this type of material. So what we did is we compared different measurement porosity techniques, like gravimetric measurements, CT scanner, optical, SEM, and tensile test, and try to provide few guidelines in order to measure the porosity of this material efficiently. So we encourage you to have a look. It was a small apartheid out of actuators, but it's important because it influences the actuation as well. So there is a paper that gives that kind of guideline if you're interested. Now I'm going to go a bit back to actuation and talking about speed. So the speed of actuation is interesting because depending on the function of your material, there are different speeds that are available. So you can want a material that reacts quickly, so it's very reactive. And in this case, you want the derivative of the curvature against time in order to be able to know at what time how your material is moving, how fast it's moving at a given point. However, if you are looking for sequential actuation, so you have two materials and you want one to arrive before the other one, you need to know the value of tau in this graph, which represents the time of convergence in an interval of a given percentage towards the final value of actuation. And so depending on what you want, you might want one or the other of the parameters. So an example of the test that we've done in order to measure that kind of speed reaction of our materials is a material that we position in a box with Petri dish, so at 98 relative humidity. Then you have two cameras on both sides of the specimen. And as you can see on the photo, you have little trackers along the specimen. And we track the position of these little trackers in order to be able to interpolate a circle around with all these different points and obtain the curvature of this specimen by this measurement. Then we plot the curvature against the time, and from this graphs in D, we are able to measure the reactivity of the speed of actuation, but also the time of convergence for our material. So it's the same specimen that I've presented before. You have three different layers. One is horizontal, and two have an angle, basically an angle alpha for the printing path. So the blue line that you see are the printing paths for the material. So, and we wanted to see what kind of value of alpha we can use in order to change the speed of actuation of our material. So we plot the curvature kappa against the time at the bottom of the screen, and you can see that the time of convergence for the 40, 45, and 50 degrees specimen for the value of alpha are longer to converge than any other one. And so basically, if you want a sequential actuation with different material arriving at a given time, you might change your value of alpha in order to know which one is going to arrive first, and then which one, and then which one. So they were the longest to converge, the 40, 45, and 50, but they were also the most reactive. So initially, we measured the speed, and the speed of these three specimens was the highest. And so if you want a reactive material, in order to trigger, for instance, a signal, and you want it to be triggered quickly, you might want that kind of value of alpha in order to be quick, this material. That was the speed, but another parameter which is absolutely key when you're doing actuation is the reversibility. So in the literature review that we're talking about in advanced functional material, we define reversibility as a three-step process. First, you have a reference of actuation, so you condition your specimen in relative humidity alpha. Then you give it an actuation history. You condition it for N1 relative humidity for N2 repeats during N3 days, weeks, minutes, seconds, depending on the actuator you have. And then you condition it back to alpha in order to measure the deformation again. You have kappa F, kappa I, you compare these two curvatures, and you are able to know how your material is repeatable. So we have not published the data of reversibility that we've measured yet, but we created a database because this type of parameter, as you can imagine, there is an infinite number of actuation history that you could provide your material in order to see if it's repeatable or not. So providing the database is key because you are able to see what are the critical tests to conduct in order to know if your material is repeatable or not. And so this database is available in this literature. If you're interested, it's very, very interesting papers that we highlighted in here. So another aspect which is absolutely key for us is the modeling. How do you model an actuation? So there are 4 different groups of modeling that we've highlighted: Timoshenko, classical laminar theory, FES, generic FEA, elastic energy methods, and voxel-based methods. So first, Timoshenko is a bilayer structures equation, analytical equation that you can see on the right side of the screen, which is related to the properties of the layer that you're considering. So you have 2 layers with different thicknesses and stiffnesses. If you have this property for your different layers, you can implement it in your Timoshenko beam equations and get a rough estimate of the actuation that you will get at the end. So you can have a bit more complexification for this model. For instance, once we decided to build a model of Timoshenko joined together one after the other, and therefore we could understand the deformation of materials in which the properties of the material was changing along the length of the actuators. So this more complexified version of Timoshenko is available in the paper we published in additive manufacturing in the supplementary section, if I'm not mistaken. So that's the first technique. Second technique is classical laminar theory, which is very standard for composite filaments. If you have straight fibers with asymmetric stacking sequence, then you are able to have a quick estimate of the curvature that you will get from classical laminar theory. FEA does the same thing for composites, and it's especially interesting for beam material structures because you can have different distribution of your material and see how the distribution of your material create the actuation. But it's much more complex if you want to have a complex printing path for composite actuators. For such more complex printing path, and elastic energy methods and voxel-based methods are interested because you are able to understand locally how your material behaves. So that's one thing that we wanted to do is create a FEA model which is able to understand complex printing path. So we wanted to have an actuator that could be used in order to understand this behavior. So we used leaf basically because leaf, when they drop from the tree and they are on the floor, they tend to curl. Well, certain of them tend to curl. And so we wanted to reproduce that kind of curling of leaves in our material. So what we did is we look at the vein pattern at the back of the leaf, as you can see on figure B. Then we try to reproduce that vein pattern so that the printing path in figure C. And then for the second layer, we wanted a sort of a printing direction, which is transverse to the first layer, and that's figure D. Then we printed the specimen, conditioned them between 11 and 98% relative humidity, and then with digital image correlation, obtained the 3D deformation of the specimen at all time. So that's for the specimen, we have its deformation. Now we wanted to create a model capable of understanding such printing path. What we did is we took the image C and D, so the printing path, and we turned it into images. From these images, we obtain the local fiber orientation and fiber volume fraction to the amount of material locally. So that image B and C on the right side of the screen. And from this, we have the property of the material and the deformation responsive properties from humidity of the material. And so we could obtain the mechanical properties and the fiber orientation locally for the printing path. Then we implement a FEA model in which we assign each element, each property locally, basically, for each element. And therefore, we are able to have a material actuating, which is representative of the local printing path for the material. It's an interesting model because you can also link the curvature that you obtain at the end with the printing path that you have. So as you can see in figure C and D on the left side of the screen, we parameterize our printing path, so you can link the final curvature that you get with this parameter and optimize the printing path from the curvature that you want with an optimizer, such as the genetic algorithm, for instance. So this model, we compared the results that we obtained with the tests that we've done. We were not fully satisfied with the comparison, and we explained the different sources of difference that we obtained between the model and the test. But this model was also very interesting for us because we were able to understand the local, where the actuation comes from on the specimen. So we are back to the specimen that we tested with the angle alpha, first layer transverse and two alpha and minus alpha layers. Then I present here, so the model that I've just explained for the alpha equal 45 and alpha equal 85. And so FEA model is, so in these figures, you can see that the blue is low amount of stresses, where the more it becomes red, the higher the stress is. Basically, the greenish point that you see on the top and the bottom graphs represents the local point where there is actuation happening, which triggers the overall actuation of the material. And so the model that we've described before is capable of telling you exactly where are the points where the actuation is coming from, and therefore you can change your fiber path if you want the actuation coming from different points, basically. So an example is a 45-degree specimen. The actuation mostly comes from everywhere around the specimen, whereas the 85 degrees specimen, the stresses are mostly located on the edges, and therefore the actuation comes from here, mostly. Although you can have a look at the different scale, they are not exactly the same, so it might differ depending on the value of alpha that you implement, basically. Another aspect that we wanted to try is to make a bit complex, another complex shape. So we wanted to get inspired by the KLED flower, which is an interesting flower because it's very curved and doubly curved. So you want to try to obtain from a flat surface after 3D printing a doubly curved flower. So we 3D printed the image on the left, so that's the printing path that we implemented. And then we tested exactly the same way as a leaf, between 11 and 98% relative humidity. We obtain the actuation, as you can see in images B and E. And you can see that there is not a lot of actuation that we could obtain. So we wanted to understand how could we improve the actuation and control the actuation as well. And so that's the first reason for the specimen that I've been, we got interested in throughout this presentation, is what value of alpha is the optimal in order to increase the actuation. Because in a lot of papers, the stacking sequence that is used is a cross-ply stacking sequence, meaning you have first layer 1 is the same, and then you have a layer which is longitudinal, which is at 90 degrees, from the first layers. I wanted to know if a value of alpha can improve this amount of actuation. So from we are able to see that between 40, 45, and 50 degrees, we are able to increase the amount of curvature we obtain for the specimen. And so improving the KLED flower design would be to change the relative angle between the two different layers locally to improve the amount of actuation we can get. Another specimen that we wanted to try is having, instead of a cross-ply straight fiber layers, we wanted to curve one of the layers. So you can see on the left, the first layer is curved and the second layer is straight. And so we wanted to know by curving the fiber, we can control the actuation. So we printed the specimen, tested them, conditioning between 11 and 98 once again, DIC to obtain a 3D view of the specimen in time. Then as the specimens are circular, we were able to define AOM, which are angle of measurements, which are different angles around the specimen in order to obtain the curvature for the different angles around the specimen. So we obtained this curvature and plotted the curvature against the angle of measurement and the time, basically. And then we were able to see from this test that the more you curve your specimen, the lower the amount of actuation that you will get. And therefore, you can also control the amount of actuation by not curving your specimen, by keep them straight, basically. That's also one of the design aspects that could be implemented in order to design further more complex geometries. Another aspect that we wanted to discuss is, you can see the image in this figure. There is, all the fibers are very compacted onto each other, basically. So they are joined onto each other for both layers. And we are wondering, is it possible to have an actuator in which the fibers are not compacted onto each other, and you just have contact point in which the actuator is happening, and the rest is a sort of lattice structure. So that's one of the aspects that we wanted to discuss is to do it with alginate polyoxame hydrogel. And that's what we did. So one of the materials we tested is alginate polyoxame hydrogel in order to know if we can have contact points, basically, for our material. There is one test which is interesting to do, is the collapse test. And there was no clear standardization of the collapse test for very soft material like the one we were using. So we took the opportunity of generalizing the measurement of yield stress in collapse test, and we published a paper about it. This collapse test basically are able to tell you if your material is able to print without support between 2 points. So it's related to our idea of printing a material and only have contact points between the 2 different layers and not have fully formed layers as actuator. And then we sort of implemented some of, so that kind of idea of having layers which are not fully compact onto structures as seen, which is inspired by flower, in which you have a concentric layers of the first layer. So concentric circles as the first layer. You can see that the concentric circles are distant from each other. And so you need to be able to print onto the first layer without your material failing. And so that's what we did. And you have to imagine that on this actuator, all the actuation is controlled by the contact point between each different layers and the orientation of the material at this contact point. And so you can, if you modify the position of your contact point and the angle of the material, you can obtain some fairly complex actuation, such as the one that we present on this video. So yes, this was made with flax fiber reinforced alginate polyoxame. So I'd like to thank you for your attention. So this presentation and most presentation for the paper is available on the YouTube channel. And thank you to all my supervisors, Antoine, Adam, James, Fabrizio, and David, who helped me a lot. And thank you to Ecotech Milan for helping us with the material, ERC, EPSRC, and DSTL. Don't hesitate to ask any questions in the comment if you have any. Thank you very much.